Hi everyone, welcome to this chapter TCP flow control, window size, and acknowledgement. TCP also provides mechanisms for flow control. Flow control is the amount of data that the destination can receive and process reliably. Flow control helps maintain the reliability of TCP transmission by adjusting the rate of data flow between source and destination for a given session. To accomplish this, the TCP header includes a 16-bit field called the window size. The figure shows an example of window size and acknowledgement. TCP window size example. Okay. MSS maximum segment size. During three-way handshake, window size 10,000 MSS, 1000 for 16, send Windows 10,000 from PCB to PCA. Sequence number 1, receive 121 for 60, and sequence number 1 for 61, receive 1 for 61, 2 to 920. Receive acknowledgement send window 12,920, Act 2 921, window size 10,000, and sequence number 2921, 1 for 60 bytes, receive 2920, 2 for 380, receive acknowledgements and Windows 4380, window size 10. And the window size determines the number of bytes that can be sent before expecting an acknowledgement. The acknowledgement number is the number of the next expected byte. The window size is the number of bytes that the destination device of a TCP session can accept and process at one time. In this example, the PCB initiate window size for the TCP session is 10,000 bytes. Starting with the first byte, byte number 1, the last byte PCA can send without receiving an acknowledgement is byte 10,000. This is known as the send window of PCA. The window size is included in every TCP segment so the destination can modify the window size at any time depending on buffer availability. The initial window size is agreed upon when the TCP session is established during the three-way handshake. Three source devices must limit the number of bytes sent to the destination device based on the window size of the destination. Only after the source device receives an acknowledgement that the bytes have been received can it continue sending more data for the session. Typically, the destination will not wait for all the bytes for its window size to be received before replying with an acknowledgement. As the bytes are received and processed, the destination will send an acknowledgement to inform the source that it can continue to send additional bytes. For example, it's typical that PCB will not wait until all 10,000 bytes have been received before sending an acknowledgement. This means PCA can adjust its send windows as it receives acknowledgement from PCB. As shown in the figure, when PCA receives an acknowledgement with the acknowledgement number 2921, which is the next expected byte, the PCA send window will increment to 920 bytes. This changed the send windows from 10,000 bytes to 12,920. PCA can now continue to send up to another 10,000 bytes to PCB as long as it does not send more than its new send windows at 12,920. A destination sending acknowledgement as it processed by receipt and the continual adjustment of the source send window is known as as sliding window. In the previous example, the sending window of PCA increments or slide over another two 921 bytes for from 10,000 to 12,920. If the availability of the destination buffer space decreases, it may reduce its window size to inform the source to reduce the number of bytes it should send without receiving an acknowledgement. Note: devices today use the sliding windows protocol. The receiver typically sends an acknowledgement after every two segments it receives. The number of segments received before being acknowledgement may vary. The advantage of a sliding window is that it allows the sender to continuously transmit segments, as long as the receiver is acknowledged previous segment. The details of a sliding window are beyond the scope of this course. The next point is TCP flow control maximum segment size. In the figure, the source is transmitting 1 for 60 bytes of data within each TCP segment. This is typically the maximum segment size that the destination device can receive. The MSS is part of the options field in the TCP header that specifies the least or the large amount of data in bytes that a device can receive in a single TCP segment. The MSS size does not include the TCP header. The MSS is typically included during the three-way handshake. Okay, this is the process. And a common MSS is 1 for 60 bytes when using IPv4. A host determines the value of its MS field by subtracting the IP and TCP header from the Ethernet Maximum Transmission Unit (MTU) on an Ethernet interface. The default MTU is 1500 bytes. Subtracting the IPv4 header of 20 bytes and the TCP header of 20 bytes. The default MSS size will be 1 for 60 bytes as shown in the figure. Okay. Okay. TCP flow control congestion avoidance. When congestion occurs on a network, it results in packets being discarded by the overload router. When packets containing TCP segments do not reach their destination, they are left acknowledged by determining the rate at which TCP segments are sent, but not acknowledged. The source can assume a certain level of network congestion. Whenever there is congestion, retransmission of lost TCP segments from the source will occur if the retransmission is not properly controlled. The additional retransmission of the TCP segment can make the congestion even worse. Not only are new packets with TCP segment introduced into the network, but the feedback effect of the retransmitted TCP segment that were lost will also add to the congestion. To avoid uncontrolled congestion, TCP employs several congestion handling mechanisms, timers, and algorithms. If the source determines that the TCP segments are either not being acknowledged or not acknowledged in a timed manner, then it can reduce the number of bytes it sends before receiving an acknowledgement. As illustrated in the figure, PCA sends there is congestion and therefore reduce the number of bytes it sends before receiving an acknowledgement from PCB. TCP congestion control. I'm not getting the acknowledgement I expect from PCB, so I will reduce the number of bytes I send before getting an acknowledgement. TCP segment 1 is okay, but TCP segment 2 and 3 is fail. TCP segment 4 is well, and acknowledgement segment 2. And resend the segment 2 and 3. Acknowledgement number are for the next expected byte and not for a segment. The segment number used are simplified for illustration purpose. Notice that is the source that is reducing the number of acknowledgement bytes is sent and not the window size determining the destination by the destination. Note explanation of actual congestion handling mechanisms, timers, and algorithms are beyond the scope of this course. Finish with check your understanding. Question 1. What field, what field is used by the destination host to reassemble segments into the original order? Repeat the question. What field is used by the destination host to reassemble segments into the original order? Sequence number. The sequence number field is used by the destination host to reassemble segments into the original order. Question 2. What field is used to provide flow control? Window size? I don't know. What field is used to provide flow control? Flow control, control bits, or window size? I say is window size. That's right. The window size field is used to provide flow control. Excellent. What happens when a sending host sends there is congestion? The receiving host increase? No. The sending host increase the number of bytes. The sending host reduce the number of bytes it sent before receiving an acknowledgement from the destination host. That's right. When a sending host sends congestion, it reduces the number of the bytes it sent before receiving an acknowledgement from the destination host. The next topic is UDP Communication, UDP Low Overhead versus Reliability. As explained before, UDP is perfect for communication that need to be fast, like VoIP. IP. This topic explains in detail why UDP is perfect for some types of transmission. As shown in the figure, UDP does not establish a connection. UDP provides low overhead data transport because it has a small datagram header and no network management traffic. UDP does not establish a connection before sending data. UDP Datagram Reassembly, like segments with TCP, when UDP datagrams are sent to a destination, they often take different paths and arrive in the wrong order. UDP does not track sequence number the way TCP does. UDP has no way to reorder the datagrams into their transmission order, as shown in the figure. Therefore, UDP simply reassembles the data in order that it was received and forward it to the application. If the data sequence is important to the application must identify the proper sequence and determine how the data should be processed. UDP congestionless and unreliable. Different datagrams may take different routes. Okay. Data is divided into datagrams. Datagram 1, 2, 3, 4, 5, 6, having taken different routes or the destination datagrams arrive out of order. Out of order datagrams are not reordered, lost datagrams are not resent. Okay? UDP server process and request. Like TCP-based application, UDP-based server applications are assigned well-known or registered port numbers. As shown in the figure, when this application or process are running on a server, they accept the data match with the assigned port number. When UDP receives a datagram destined from one of these ports, it forwards the application data to the appropriate application based on its port number. UDP server listening for request. Okay, DNS request client 1 to the server and client 2 radius request. Server application client DNS request will be received on port 53 and client radius request will be received on port 1812. Okay. UDP client process with TCP, client server communication is initiated by a client application that requests data from a server process. The UDP client process dynamically select a port number from the range on port number and use this as the source port for the conversation. The destination port is usually the well-known unregistered port number assigned to the server process. After a client has selected the source and destination port, the same pair of ports are used in the header of all datagrams in the transaction. For the data returned to the client from the server, the source and destination port number in the datagram header are reserved. Select each tab for an illustration of two host requesting service from the DNS and Radius authentication server. In the first tab is client sending UDP request. Client 1 is sending a DNS request while client 2 is requesting Radius authentication service of the same server. We can see client 1 DNS request, source port, destination port, and the case of client 2 Radius user authentication request, source port and destination. Both send information to the server. In the step 2 UDP request destination port, client 1 is sending a DNS request using the well-known destination port 53, while client 2 is requesting Radius authentication service using the registered destination port 1812. Okay, the client requests the UDP server to use well-known ports number as the destination port. Destination port is a known port number. The next step, UDP request source port. The request of the client dynamically generates source port numbers. In this case, client 1 is using source port 49152 and client 2 is using source port 51152. Source port. Use random ports numbers as the source port. The next step is UDP response destination. When the server responds to the client request, it receives the destination and source port of the initial request. In the server response to the DNS request is now destination port 49152 and the Radius authentication response is now destination port 51152. And port response, okay. Client 1 waiting for server DNS response and client 2 waiting for server Radius response. And the last step is UDP response source port. The source port in the server response are the original destination port in the initial request. Server DNS response source port 53, destination port 49152, and client 1 client waiting for the server DNS response on port 49152 and server Radius response source port 1812, destination port 51152, and client 2 waiting for the server Radius response on port 51152. Finish with the questions. Why is UDP desirable for protocols that make a simple request and reply transaction? For low overhead. UDP is desired for protocols that make simple request and reply transactions because of its low overhead. The next, which UDP Datagram Reassembly statement is true? Repeat the question, which UDP Datagram's reassembly statement is true? Sorry, reset. And UDP reassembled the data in order that it was received. The next question, which of the following will be valid source and destination ports for the host connection to a DNS server? Source port, destination port. The correct valid source and destination port for a host requesting DNS service is source 49.152, destination 53. And finish with transport layer summary. Okay, this is for the next one.